Okay, today we will discuss the experiments and quasi-experiments. Why should we use the experiments? In many fields, we use the experiments to evaluate the causal effects. An ideal random control experiment provides the causal effect from the observational data. So it's important to understand the experiments. And sometimes we assign a treatment group and a control group, and sometimes because of the external events, so the randomness possibly conditional on some control variables. We will discuss this topic in the last session in this chapter. It's about the quasi-experiments or natural experiments. Let's start to the potential outcome, causal effect, and ideal experiments. What is the potential outcome? The potential outcome is the outcome for the individual under the potential treatment. So we should have a treatment, and we evaluate an individual. And the causal effect for the individual is the difference between if the outcome in the treatment or the outcome not have the treatment. However, the individual either receive the treatment or not receive the treatment. So we cannot measure the causal effect for a single individual. So what can we do? We can use the average treatment effect. What is the average treatment effect? The mean of the individual causal effect in the population under study. So we use the average to solve the problem for the individual causal effect. Because we cannot evaluate the individual causal effect, so we use the mean to solve this problem. And in this structure, we should have the two conditions. The first condition is about random selections. We should random select the subject from the population. Second is about the random assignment. So we should random assign the subject to the treatment group or the control group. And in mathematics, we can use the expectation. Okay, so here is a typo. Xi equal to 1 is mean the subject have the treatment. So in the treatment group, and Xi equal to 0 is mean in the control group. So if we can calculate these two expectations, make a difference. It's the average causal effect or average treatment effect. They are the same. And the individual causal effect maybe depending on the observable variables or non-observable variables. So we should use some method to evaluate the average causal effect. The first, we use the difference estimator to evaluate the average treatment effect. We consider linear regression here. Y equal to beta naught plus beta 1 times xi plus ui. It's like a simple linear regression. Where is yi is the outcome variable and xi is the treatment indicator. So when in the treatment group, xi is equal to 1. In the control group, xi is equal to 0. And we can find the difference estimator is the beta 1. It's a sample average for the treatment group and the control group. If the xi is random aside, then the given xi, the mean of ui is equal to 0. And beta I hat is an unbiased and consistent estimator for the causal effect. So we can derive it for the, so we use this model setting. Y equal to beta naught plus beta 1 times xi plus ui. And we can find given xi equal to 1 minus xi equal to 0, the conditional expectation. We have a difference about this term is equal to beta naught plus beta 1, and this term plug in a xi equal to 0. So here is 0. The conditioning of xi is equal to 0. So we know this is only one term is beta naught. So here we can have the beta 1. It's the average treatment effect or average causal effect. Okay, so we have to make a difference estimator as the average treatment effect. Sometimes we consider more control variables. So we can plug in add into wi. So in here is about a control variable. So in this model setting, if w helps implement the variation in y, then we can reduce the standard error of the beta 1. Well, it is by the formula for the standard error of the beta 1. Okay, so if the wi is a pre-treatment characteristic and xi is random assigned, then the conditional mean independence is valid. So we can have this condition. That is to say xi is independent of the ui or the wi. Under this condition, the coefficient on the control variable, unfortunately, this coefficient, we cannot have the causal interpretation for the control variable because we only focus on the interest variable xi. We only focus on here, not here. Okay, Next, we can consider the interaction term. When the interaction term including some covariates like xi, wi times wi, it's like covariates. So covariates is like regressors. You can consider the different regressors, combine different regressors as one interaction term. So if the treatment effect is the same for wi equal to 1 or wi equal to 0, then we can don't use the interaction term because the treatment effect for these two groups, they are the same. But if the treatment effect is different for these two groups, in this situation, we should consider the interaction term for xi times wi because the treatment effect is different. Okay, so it's a model setting problem. So you can use the model to do in your programming software like R to do this. So now we discuss the threats to the validity of experiments. At first, we discuss the threats to the internal validity. And some reason have these threats to the internal validity. One reason is about the failure to the randomize. So we don't have the random assignment or random selection, so we cannot have the internal validity. So how can we test this situation? We can run this regression xi on W1, W2 to WR, and we consider a null hypothesis is about if this delta 1, delta 2, delta R, and null hypothesis is about delta 1 equal to delta 2 to equal to delta R equal to 0. We can do this test. It's a joint coefficient test. You can find an F statistic to make a conclusion. So if we reject this null hypothesis, then we don't have a random assignment or random receipt of the treatment. Okay, so we can do this test to check the randomization. Next, failure to follow the treatment protocol. So in this situation, sometimes the people don't follow what they said, so we cannot convince what they told. So we can use some method to evaluate this situation, like a IV estimation. Okay. And in this situation, because this condition is valid, so the conditional mean of the error term is not equal to 0. So we should deal with this problem. And solution is about the IV. So we can use the IV to evaluate the treatment effect. How about attrition? Attrition is mean like a subject dropping off of the study after the random assignment. So like for example, in a school, one day we have a new student, a new transfer, new student to add in our class. But tomorrow, the student doesn't like this class, so he want to transfer to a new class. So this is invalid for the attrition. This is attrition. So we cannot have we should do some adjustment to evaluate the treatment effect. Next is about experiment effects. So what is the treatment effect? Subject under the experiments can change their behavior. So in a treatment group, they will have some characteristic, and in a control group, they will have the habit to do something. So we cannot have. So this is about treatment experiment effect. So we can like to see this. So we can use the double-blind protocol to mitigate the effect of being in the experiments. This method is used under the medicine, so like a vaccine. So if the experiment is double-blind, both the treatment and control groups should experience the same experimental effects. So different outcomes between these two groups can be attributed to the drug. So this method also is used to the medicine. But we don't use this method in the social experiment because they have some problem. And in the end, we should consider the sample size. If the sample size is too small, although we don't have a bias, but the causal effect is not precisely, so we should consider how to get a large sample. How about the external validity? If we have the non-representative sample or non-representative program or policy, or in a general equilibrium effect, we refer to the external validity. So this problem we also discuss in a micro or in between a micro and a macro. So they are similar to each other. So now we see the example of the STAR project. It's about the experimental. We want to see the effect of the class size reduction. Okay. This project is about is named STAR, Student-Teacher Achievement Ratio. It's about a 4-year experiment. to evaluate the effect on the learning of the small class size. The study compared 3 different class arrangements, and for the 4 grades: kindergarten, grade 1, grade 2, and grade 3. The first class arrangement is about a regular size class with 22 to 25 students per class. Have a single teacher and no teacher aid. Second is about a small class with 13 to 17 students per class and no have a teacher aid. And third is about a regular size class with a teacher aid. So we should consider class size and a teacher aid. So in this experiment design, we randomly assign these 3 groups. And the teacher also randomly assigned to each class. And how about a deviation from the experimental design? The experimental protocol specifies that the students do not switch between the class group except the re-randomized at the beginning for the first grade. So we should consider the attrition to this problem in this experiment. And the class size change over the time because the students switch between the class and move in or move out to the school districts. So it is also a problem for the attrition. So we should solve this problem. And see the model setting. We consider this population regression model. We use the 2 treatment indicator: small class and a rich and the regular class 8. We have the 8. When the beta 1 and when the small class equal to 1, it means student in a small class. And a regular class 8 equal to 1, it means the student in the regular class have the 8. Okay, so and because the cluster standard error allows for a correlation between the school or entities, so we compute a standard error with a cluster at the school level. In this model setting, we use the cluster standard error because the different score have the correlation. Okay, at first we should import the data set. Because this is a data file, so we should use a foreign like package. So we call the foreign, use the library command, and set a path to the R, and read the DTA, and pass the file name, read the data. For the kindergarten, we use the t-score. It's like a y. And here is about x. I think it's like a small class reach 8. small class reach 8. Okay, so here's about y x1 x2. So we do the LM, linear regression, and here, because we want to calculate the cluster standard error, so we should call the package about LM test and multi-wave VCOV. It's about a cluster VCOV in this package. So we should call these two packages in R. And here we find a robust standard error, robust cluster standard error here. So we have these to plug in a model, and here's a model. And write down the cluster we want to use, because we want to use the score level as the cluster, so we should use this variable. Okay, because here we use a kindergarten, so we use a K. Next, the first grade. So we change to 1. Here is about 1. So we do the same thing, similar thing, but change the grade for the data. And next, we also do the similar thing, change the grade. Okay, so do the same. Next, about third grade, change the grade level. Okay, and remind. I should remind you, because in our data set we have some missing value, so we should use this command NA omit. It means we omit the NA, we omit the missing value. So this is very important. If we don't type this comment in LM, this comment cannot implement, cannot have the linear regression result. It has some warning in R. Okay, and next we combine these two models in one table. Kindergarten, first grade, second grade, third grade, and assign the cluster standard error. And here I name the covariates for each. Okay, and I also name the dependent variable. Here we can see this. Here is about dependent variable. It's like a y. About x1, x2. Okay. So for kindergarten, you can see here the small class, the coefficient of the small class is significant. For the first grade, also significant. So for each grade, for the coefficient on the small class, they are significant. In the regular size class with 8, unfortunately, only first grade, only this coefficient in the first grade is significant, and this 3 is not significant. So maybe we should argue this variable. So we argue maybe we have some more efficient estimate. So we should have some additional regressors in our model. And if the treatment received is non-random, because sometimes we have some problem for the treatment protocol, then the estimate of the experimental effects could differ from the difference estimate in this table. So we should consider these two problems. One is an additional, maybe we should consider some additional regressors or the failure for the treatment protocol. And here we consider more regressors. And first, we do the same for the kindergarten. In the table 15.2, we consider in the kindergarten. So we should use K. And here is the same for the first column in the table 13.1. And here we plug in new regressors. And here we use plug in the score level. And next we plug in some regressors: gender, free lunch policy, and the race. Okay, we also do the same thing for plugging these four models in one table. And here we define a Y. And here is about X. Okay, see a result. So now we can see this result. In the original model setting, we only consider these two regressors: small class and a regular size class with the 8. So here is significant, but here is not. And in the second model, we consider Detroit experiments is significant. But we argue maybe the teacher experiments is related to the score digits. So we plug in a score indicator. If we plug in a score indicator, you can see the adjusted R-square increase. So maybe we should consider the score indicator. And next, we want to consider more regressors. So maybe in the gender for a boy, free lunch policy, and a race. So we can see this significant, also significant, and here is not significant. Okay, so this is about table 15.2. Next topic is about a quasi-experiment. So we talk in this topic. In a quasi-experiment or a natural experiment, randomness is introduced by the variation in the individual situation that may appear as if the treatment is random assigned. So it's not random assign, but it's as if random assign. It's like a random assign. Because these variations is maybe related some variables. Okay, so these variations in the individual situation is not, it might arise because the factor not unrelated to the causal effect under study. And here is two types for the quasi-experiment. The first type is about whether the individual of the entity received the treatment is viewed as the random determined. So in this type, the causal effect can be estimated by the OLS. And use the Xi as the regressors. And the second type is about as if random variation only partial determines the treatment. So this type is only partial determined by the treatment. So the causal effect should determine by the instrumental variables like the IV, whereas the as is random source of variation provides the instrumental variable. So we should use the instrumental variable to transfer this form to like a first type. Here's some example. Labor market effects of the immigration, or the effects of the class size on the educational achievement, like a above section topic. The effect of the cardiac catheterization is like some medical issues. Here, we use the difference. The first estimate is about the DID. Difference in difference. DID. Or DD. Sometimes we use the DD or DID. They are the same. If we consider these linear regressions, so here is about the change of the y outcome variable after and before. So here's about y after minus yi before. We consider one regressor. It's a binary treatment indicator. So how about the difference-in-difference estimator? We denote it by this beta 1 hat DID or DD. It's defined by the y bar hat treatment after the treatment minus y bar before the treatment and minus the y bar delta y bar for the control group. Here is about delta y bar for the treatment group. Here is about a y bar, delta y bar for the control group. So we evaluate these two terms, the difference between these two terms. Okay. If the treatment is random assigned, then the difference-in-difference estimator is an unbiased and a consistent estimator for the causal effect. Sometimes we should consider more regressors. So we combine it, we plug in this control variable. And the beta 1, we can do the same thing for the difference-in-differences estimator with the additional regressors. This additional regressors is like a control variables. And if the xi is as if random sign, conditional on the control variables, then ui satisfies conditional mean independence. And beta 1 hat is unbiased. Here we see the one example. It's about one research in the 1995. This research is about the length of the time left injured worker receive the worker compensation. We want to check an increase in the cap is like a duration have no effect on the benefit for the low-income workers, but it makes it less costly for the high-income workers to stay on the worker compensation. So we want to check this thing. And here we design the experiment. For the control group, it's a low income, and the treatment groups is a high income. Okay, so high income workers are defined as those who were subject to the pre-policy change cap. We consider this model setting. The log duration in log as the y, and we consider this after change is a dummy variable for observation after the policy change. So if the after change equal to 1 is after the policy or treatment, and if the after change is 0, it's like a before the treatment. And a high earn equal to 1 is in the treatment group, because the low income is a control group and the high income is a treatment group. Okay, and we should consider the interaction term, because this term is about the DID estimator. And this example is from the famous textbook by Woodridge. So we should, and this dataset in the also built in the R package is named Woodridge. It's an awful name. Okay, so at first we should library this dataset package Woodridge, and this dataset named the injury. So we use this data and we plug in the model log duration after change, higher earning, and the interaction term. Because we want to calculate the robust scenario, so we should use a sandwich package. And we have the output in a one table. Here we can see this result. So here you can see this variable is not significant. This is significant for the high earning. Interaction also significant. Okay. So here is about beta DID. Why? In this model setting, it's like this. Here I use a F H A H A times H. Okay, I use this free variable notation. Okay. I don't use notation for the observation I. And here, consider these three things. The treatment after the treatment. Okay, we can see is it's about delta y bar treatment, delta y bar control. So here is about delta y bar treatment minus delta y bar control. At first we should find out y bar. Beta 0 plus beta 1a plus beta 2h plus beta 3a times h. The first term is like after treatment is like a and h is equal to 1. So we plug in here beta 0 plus beta 1 plus beta 2 plus beta 3 and minus. Okay, before the treatment, it means Heineken is the treatment, so here's a 1, but here's about before, so this is 0. Beta 0, beta 0, beta 2. Okay, so it is a beta 1 plus beta 3. About the first term. How about the second term? Delta y bar for the control group. After the control group, control is here is h is equal to 0. Beta 0, beta 1. And before the control group is about here's 0 and 0, so only beta 0. So here is only beta 1 for second term, and here we'll make a difference, so only have the beta 3. So the DID estimator is beta 3 in this model set. So we can see this, the DID estimator is significant. Here we see the interpretation. The beta 3 hat implies the average length of time on the workers' compensation for a high earner increased by about 90% due to the increased earning gap. However, the coefficient of the after change is very small, and the statistically insignificant as our expectation. Increase the inner earnings gap have no effect for a low income worker. So this result makes sense. This result also makes sense. Okay, so this is about this research from the Woodridge textbook. And next is about an Instrumental Variable Estimator. So if the Zi is a valid IV for the Xi, the coefficient can be estimated by the two-stage least square. Okay, so and we should have these three conditions. The first condition is about the quasi-experiments. It's yes, a variable Ci. Let's influence the treatment. And the data are available both on the Ci, on the treatment actually received Xi. And the third condition is about the Ci is about as if the random assignment. So we should have these three conditions valid. Then we can use the IV to do the two-stage least square to estimate the causal effect. Next topic, Regression Discontinuity Estimator. So because of the jump or discontinuity in the treatment after the threshold or cutoff, we should study the discontinuity in the probability of receiving the treatment after the threshold value. And it is called the regression discontinuity design. Sometimes we call this is about RDD or RD. There are two types of regression discontinuity design, sharp RD or fuzzy RD. Sharp or fuzzy. They are different. At first, we should see one example. This is about one research about elections in US. So I use this data set to do the RD plot. It's about regression discontinuity plot. So we use a ADS score as the y-axis, and the x-axis is about a democratic vote share. Okay, and here I choose the cutoff or threshold. You should use the threshold in our model setting, our plot setting. Okay, so we can see this plot. Because in the paper, the authors use a polynomial in 4 degrees, so I use 4 degrees in this plot. So we can see here in the threshold or cutoff, there is the discontinuity. Okay, so maybe we should discuss the reason in the threshold. The first type is about sharp RD. The sharp RD is defined by the probability of the getting the treatment jumps from 0 to 1 or 1 to 0 at the cutoff. And we consider linear regressions yi and xi, wi. Y is the outcome variable, and xi if the w greater than w0, then xi equal to 1. And if the w less than the w0, then xi equal to 0. Maybe we can use another model setting, maybe xi equal to 0. Maybe you can use this different model setting, but you should follow this definition. The probability of getting treatment. One group is greater than a threshold. Or threshold or cutoff. One group is greater than threshold, and the other group is lower than the threshold. So maybe here's 1 and here's 0, or here's 1, here's a 0. Only two situations for a sharp RD. However, if the probability of getting the treatment is not jumped from 0 to 1, but they are jumping at the cutoff, is a fuzzy RD. So it means someone follow the treatment assignment rule, but someone doesn't follow the treatment assignment rule. That is to say, some individual above the cutoff do not get the treatment, or some individual below the cutoff receive the treatment. So, for example, like this, maybe here. So here I use a cutoff here. If the greater than cutoff, the probability of getting the treatment is like maybe 0.7, and less than the cutoff, like 0.3. Okay, this is an example for the fuzzy RD. The detail in the fuzzy RD and sharp RD is not in our course. So if you're interested in this topic, you can find information in another textbook. Okay, that's all for this chapter. Okay, so here is about two reference. Here's about election in US. I use this data set to demo the regression discontinuity. And the second is about worker compensation topic. I use this to demo the DID estimator. Okay, so that's all for this chapter.